Welcome to Simple Linear Regression Video 3, Sum of Squares. This video was written and produced by Elizabeth A. Albright of the Nicholas School of the Environment. This video will cover the sum of squares, and we will talk about total sum of squares explained, residual sum of squares, and the coefficient of determination, or r squared. It builds on videos 1 and 2 of Simple Linear Regression. I encourage you to watch those first before watching video 3. So here is our example from the previous two videos where we looked at the relationship between daily household income and daily household spending. On the x-axis we have daily household income, dollars per day, and on the y we have daily household spending. We have 10 observations seen in the orange points, and then we drew the best fit line through ordinary least squares. We have a horizontal line here to help us think about the total sum of squares, and I placed that line at the mean of the y observations, or y bar, and that's at 111. So what are sum of squares? Thinking about sum of squares and the different types of sum of squares, it allows us to parse out the variation in observations in a sample. So there's total sum of squares, there's explained sum of squares, and unexplained sum of squares, or residual sum of squares. And then this allows us to talk about the goodness of fit of a model to the data, or to the observations. And in this video we'll talk about r squared. So total sum of squares, or total variation. This is the sum of the difference between the y observed and the y means, those differences squared, and then summed. So those differences between yi and y mean, or y bar, are shown in green. Right? The lines, the green lines, are drawn between the observed, or the orange points, to y bar, the horizontal line. Really, the horizontal line represents no relationship between household income and spending. Right? So then we square each of those green distances and sum them together, and that is the total sum of squares. We then have explained sum of squares. An explained sum of squares, or explained variation, is y hat I minus y bar, and those differences squared and then summed. Sometimes this is called model sum of squares, or regression sum of squares, but we'll call it explained sum of squares. And here in the mustard colored, you can see the line drawn between the explained, or the predicted line, and the horizontal line. So it's drawn between y hat at I and y bar. We take those differences, we square them and sum them, and that is our explained sum of squares. And as you can think, if you think about the slope of our regression line, right, and the steeper the slope, whether it's negative or positive, the greater those differences, or those mustard yellow lines would be, further away from the flat line, or the horizontal line of y bar. Right? So it would increase our explained sum of squares. And then our third sum of squares is residual sum of squares, or unexplained variation. And this is the difference between y observed minus y predicted, and those differences squared and summed. And here the residual sum of squares is in the red lines, and those should be between the observed points, or yi, and yi predicted, or the predicted y value at that yi point. So the residual sum of squares would be squaring each of those red distances and then summing them together. So what do all these sum of squares means? One, it helps us get a feel for the goodness of fit of a model to the observations. And we can do this through the calculation of what's called R squared, or the coefficient of determination. And R squared is the explained sum of squares over the total sum of squares. Right, so the explained sum of squares, if it is a larger proportion of the total sum of squares, we are explaining, or the model is explaining, a greater percentage of variation in the response. Right, so R squared is the percentage of variation in the response variable that is explained by the model. A good R squared value really depends on the context of the data, the question, the methodology, etc. We would not expect a high R squared in the social sciences as compared to a more controlled natural science experiment, for example. So in simple linear regression, R squared is equal to the square of the sample correlation coefficient. So in this figure, I have overlain the explained sum of squares, which is shown with the lines in the mustard color, over the total sum of squares. And as you recall, the explained sum of squares is the difference between the line, or the predicted, and the horizontal line, or y bar, and those differences squared and summed. And the total sum of square is the green line, which is the distance between each point or observation and the mean, or y bar. And so we could see here that the percentage of explained of total is pretty high. So let's check out R and see what our R squared, or coefficient of determination, is. So let's look at some R output. Here is the output, or the summary, of linear model 1 that I ran earlier in video 2. And we could see the multiple R squared as 0.9621. This means that 96% of the variation in household spending is explained by the model, or explained by the variation in daily income. So again, the R squared is a value from 0 to 1, and it is the percent variation in the response that is explained by the model. And that sums up this quick and short video on sum of squares and R squared. Again, this is Elizabeth A. Albright of the Nicholas School of the Environment. Thank you for listening to Simple Linear Regression Video 3, Sum of Squares.